Okay. So we'll pick up where we left off last class, which is working through proportion, hypothesis testing examples, and then we'll do a lot of work in Excel today. Something else I was going to, we'll have an online quiz today that'll have like one question. So that'll be due before class, on Wednesday, or before we start class on Wednesday. Other than that, I will be posting another Connect assignment today. So this will be the last assignment before the exam. It's just going to be hypothesis testing. So you'll be able to work through the majority of it. The parts that you can't work through will be some material that we're going to cover next class. So after next class, we should be good. And we're really just going to have a lot more hypothesis testing examples, probably Friday and Monday. And then next week, kind of start some review on next Wednesday and Friday. I'll get some practice exams up there, probably after class on Wednesday. And yeah, it'll take us kind of into that second exam. We'll get a lot of practice on these problems still. So we should feel comfortable, hopefully, by the time we get there. So let's go to where we left off. So we're doing hypothesis testing, whether or not it was for sample means where we had a known standard deviation, or we're looking at proportion examples. We said we had two approaches. The first was the p-value approach, right? So we determined the null and alternative hypothesis. We figured out what alpha levels we wanted to test at. We then calculated our test statistic, or our z statistic, because it was a test statistic coming from a standard normal distribution. We then used that z statistic to find a p-value, and that was a little bit different depending on if we had a left, a right, or a two-tailed test. Once we had that p-value, we compared it to alpha. If our p-value is less than alpha, we could reject. If it wasn't less than alpha, we'd fail to reject. Critical value approach, same two steps were identical. We could calculate our test statistic or our z statistic. We then found our critical values in our rejection region. We then said if that z statistic or test statistic was in our rejection region, we failed to reject. If it wasn't in our rejection region, if it was in our rejection region, we rejected. If it wasn't in our rejection region, we failed to reject. Right? So that was kind of the steps that we were going through. And really the only difference for when we were looking at sample means or sample proportions was this z statistic equation looked a little bit different. So I've got some kind of summary slides here. Oh, wait. Sorry. Got the wrong file open. That is what I wanted to go through. Section. Let's make sure we have the right one. Okay, yeah, so we went through these steps, but where we left off was we had kind of these proportion examples. So let's assume that I wanted to test against the hypothesis that less than 15% of Indiana mothers smoked while pregnant. So I take a pretty big sample. I got 400 mothers, 72 of them smoke, which would give me a sample proportion, 72 divided by 400, of 0.18. Okay. So what would my null alternative hypothesis be? So in every problem we've looked at up to this point, I've always kind of given you the conventional, like in the way that I'll write it on the exam, which is whatever you want to test for, right? That's your alternative hypothesis, and then you'll assume the opposite is true. So once you assume the opposite is true, that becomes the thing that you're testing against, right? So here I phrase this one a little bit differently just because we can see this when we're like looking at things outside of this class. If you're testing against a hypothesis, that means whatever you're testing against is your null. So here if we want to test against that less than 15% of Indiana mothers smoke, what we're really saying is the null hypothesis is that true population proportion is less than 0.15, right? We always include the equality in the null, so less than or equal to 0.15, and then our alternative hypothesis would be the complement of this, which would just be the true population proportion is greater than 0.15. Right? So on exams and things like that, I won't be writing it as though what you're testing against. I'm always going to say this is what you want to test for, that's your alternative hypothesis. But if you ever did see it kind of phrased as the hypothesis you test against, that is actually your null, okay? So if we have, this is our null and alternative hypothesis, what kind of tailed test do we have here? So we have a greater than sign in the alternative hypothesis, which means this is a greater than or a right-tailed test. Kind of the idea there is that if I assume the true population proportion is less than or equal to 0.15, if I see anything to the left of 0.15 or less than 0.15, that supports the null. So for sure, I'm not going to reject. The only evidence that I would reject that is if I see a sample proportion to the right of 0.15. So that's why we call it kind of a greater than or a right-tailed test. Okay. So what would my critical values be at the 1, 5, and 10% level? So if I first want to do the critical value approach and kind of think about this as, if I'm looking up critical values, those are the z values such that anything larger than those z values, if the test statistic in absolute value is larger than those critical values, then I'm going to be rejecting, right? So critical values, we had a right-tailed test, would be the z value that gives me kind of alpha in this right tail. Right? So let's say we want to look up that first alpha of 0.01. Okay? If I want 0.01 in the upper right tail, well, I'm looking at that standard normal distribution. How would I use the table to find that? Well, there's two ways we could do it. Okay? I could first say, well, when I go to that table, I know that I have to look up the area to the left, right? Well, if I want 0.01 to the right of this value, what area do I want to the left? Well, just 1 minus that, right? So I've got 0.99. I go to my z-tables. The area I want to the left is 0.99, so I got to go down a ways. Looks like it's in between these two values. So 2.32 and 2.33. I'll take the higher of the two, if we're ever in between two there. So that first critical value for the 1% level, or an alpha of 0.01, is 2.33. I could do the exact same thing, look up the other two. If I wanted the 5% significance level, that's an alpha of 0.05. So I go to the table. I wouldn't look up 0.05, right? Because that's the area that I want in my so we can think about, we just found this critical value was 2.33. If I instead wanted an alpha of 0.05, what critical value would give me that? Well, if I have 0.05, this is a 0, in the upper right tail, the area to the left of that would be 0.95. So that's what I'm actually going to look up when I go to the table. So I look up 0.95. Looks like I'm in between these two values. So 1.64 and 1.65. So 1.65. Notice that's how I find that second critical value. I can then do the exact same thing for an alpha of 0.1. I'll find that the z value that gives me 0.1 in the upper right tail is 1.29. Okay? So those are my three critical values. Now, I could have done this another way. Whatever way makes the most sense to you, I would say choose that one. But instead of kind of thinking about, okay, I want alpha in the right tail, so what area is to the left? Because when I go to the tables, I have to look up the area to the left. If I would have simply looked up alpha, so let's say I did that first one where alpha was 0.01. I wanted to find that critical value. So this was alpha. If instead of looking up 0.99, I had just said, okay, what happens if I look up 0.01? Well, if I look up 0.01 in the table, what I'm really doing is looking up what value would give me 0.01 in that left tail. But remember, if this is a symmetric distribution, it's going to be that same value, just negative. So sure enough, if I look up 0.01 in that table, I should find 2.33, whoops, but negative. So let's look up the alpha of 0.01 in between these two values. So negative 2.32 and negative 2.33. Sure enough, I found the exact same value, but negative, right?
So are those determined like whether you look on the left side or the right side by like the greater than?
Yep. If I had a left-tailed test, I would have just had to look up alpha, right? Because then I would have known I'm doing with a left-tailed test. Now, for the right-tailed test, I could look up use the same procedure, I'll find the critical values that I'm going to use for a left-tailed test, but then remember, oh yeah, but I'm dealing with the right-tailed test, so it's that same value, right? It's a symmetric distribution, so it's the same value, but my critical value is actually positive, right? Because I wanted the area to be in my upper right tail. Right? I was just kind of showing you that you can kind of use a cheat there, essentially. Instead of looking up 0.99, you could just look up alpha and remember, oh yeah, it's a right-tailed test. It's going to be positive critical values. So yeah, your left and your right-tailed tests have the exact same critical values, but for a right-tailed test, well, they're only evidence on the, we're looking at the right side of the distribution. Remember, the standard normal distribution is centered at, or has a mean of 0. So for a right-tailed test, our critical values are going to be positive, and for a left-tailed test, they'd be those same values, but negative. Okay, so we looked up those critical values. Let's see here. We had 1.29, 1.65, and 2.33. And I'll write kind of the significance levels they corresponded to underneath them, and I'll get out of the way here. Right? So those are our 3 critical values. We then said the rejection region is just going to be, if we're doing a right-tailed test, anything to the right of our critical value. Left-tailed test, anything to the left of our critical values. Two-tailed test, anything to either side of our critical values, right? Because remember, we said for a two-tailed test, we had 2 critical values. So here I have a right-tailed test, so my rejection regions are to the right of my critical values. Or I said another easy kind of theoretical way to remember this is once you have your critical values, draw arrow into the tail, right? You'll draw an arrow into the tail there. Okay. Well, now we need to know, is the sample evidence we found, will that translate to a test statistic, right, that is in my rejection region? So if I ask what the test statistic of this problem was, we go back. Well, if we remember from last class, we actually had an equation for the test statistic. Now, this is going to be an equation that you'd have on the formula sheet as we get closer to the exam, or you can kind of look it up in the slides here as we're working through Connect problems. But I'll take my sample proportion, subtract the assumed true proportion. Well, that was 0.18 and 0.15 for us, and then we had a sample size of 400. So I just plug my values in to that equation, and I get a test statistic of 1.68. Okay. So this is really, there's not a lot. Once you have the formula you've identified, you're looking at a sample proportion, you're doing a hypothesis test for it. It's a matter of getting the information you have and just plugging it into this equation. Right? There's not much I can kind of give in terms of direction for that. Okay. So what we found, we knew that our sample proportions would be normally distributed around that assumed true value, or if it is the true value, the value we assumed it was, they would be distributed around that. Now we found sample proportion of 0.18. So once we turn that into a test statistic, that was a test statistic of what? 1.68. So if I plotted that, where that 1.68 fell, notice it'd be right to the right of this other critical value I'd found. Well, notice, is it in the rejection region for the 10% significance level? Pretty clearly it is. Is it in my rejection region at the 5% significance level? Just barely, but it still is. So I can reject at the 10 and 5% significance level. Is it in my rejection region at the 1% significance level? No, it's outside that region. So I can reject at the 10 to 5%, but not at the 1% significance level, which we said would kind of translate to I can reject with 90 and 95% confidence, but not 99%. Okay? So that's how we would solve this if I use the critical value approach. What if I wanted to use the p-value approach? Well, the p-value approach says, look at that sample proportion I found. What was the probability that I saw that sample proportion or anything further away from that assumed true value? If in fact that was the true value. So I can turn that sample proportion into a test statistic. We've already done that for the critical value approach. But now I want to find the area to the right of that to get my p-value. Well, if I go to the table, it's going to tell me the area to the left of 1.68. So I can go to the table, find the area to the left of 1.68. I want the area to the right, so I would have to subtract whatever I find from 1. Right? So I go to that table, look up my test statistic, standard normal table, 1.68, so 1.6, second decimal is 8, so 1.68. The probability I saw was a test statistic of 1.68 or anything below that is 0.9535. Okay? So 0.9535, 1 minus that, I get a p-value of approximately 0.0465. So what if I had used my p-value to make rejection decisions? I'm gonna run out of room here, so I'm gonna erase this, but that's okay. So let's say we got what, 0.0435. Would that be less than an alpha of 0.1? Well, yeah, my p-value is definitely less than an alpha of 0.1, so I could reject. Would it be less than 0.05? Well, just barely, but it still is less than that alpha of 0.05, so I can reject. Would it be less than an alpha of 0.01? No. So there I would fail to reject. Which, notice, those are the same 3 decisions we made using the critical value approach. We can reject at the 10 and the 5% significance level, but not at the 1%. In fact, it's also kind of nice because, look, with this critical value, I could just barely reject at the 5% level if I look at the critical values. And if I look at my p-value, I can just barely reject it if I look at the p-value approach as well. Okay? Any questions on that? You okay with that, or try to look at the chat here too? No questions? All right. So we've got our rejection decisions. Now I'm going to kind of move into Excel. Okay, we're going to keep looking at a proportion example, but I'm going to look at it in Excel. All right. So I have these synopsis slides, which is like what we're going to do. Here's the one when we know the population variance and we're looking at a sample mean. Here's the one for proportions, and this is one we're going to do next class. Okay, so for now, we don't have to kind of pay attention to slide 11 today. So let's open up that hypothesis testing blank file. I think I left it off of Canvas prior to today's class, just so it didn't make anyone think they had to like fill it in or something. So I'm going to just upload that right now so you'll be able to kind of open that and kind of follow along, right? So after we work on this hypothesis testing blank file, it'll look similar to this hypothesis testing file. I might do a couple of additional things here in class that I didn't do here, but this complete file has like everything you would need to give you help on the Excel assignment. I might just show you a couple different things as we work through filling in this blank file. So what we're going to be doing today let's see, because right, you guys just turned in, I don't want to get you guys mixed up with my other class, but I think you guys just turned in an Excel assignment, right? Yeah. Yeah, so we won't have another Excel assignment until after the second exam. But after this second exam, we'll still be doing hypothesis testing stuff. So this is going to be relevant to like what we're doing kind of after the second exam, but also seeing it done in Excel, we're just getting more problems for hypothesis testing that get us ready for this exam. Also, like the first, I'll allow you to use Excel as you're taking the exam if you want. So if you get kind of comfortable and familiarized with how we do these things in Excel, you're going to have that tool on the exam. Okay. But yeah, there won't be another Excel assignment prior to this next exam. So let's look at a proportion example and think about how we would do this in Excel. But also, like I said, I'll switch kind of to the board as well, so we can kind of see how we would do this by hand. So we're just getting more looks at different hypothesis testing examples. So I first have entered in here a sample size. The sample is much larger, right? It's like 18,000 people. I want to show you something with a more realistic sample size that's relatively small. So let's assume that the sample is only size 100. I'll show you what happens by the end of class if we actually use the real sample size here of like 18,000. But for now, let's assume it's a sample of 100. We have this variable, which is a 1 if the person's ever tried an e-cigarette and 0 if not. This survey was of high school and middle school students, and so kind of the idea here is, well, what proportion, what's the true population proportion of middle or high school students who have ever kind of smoked e-cigs, right? So we could take the mean, or in Excel, that's the average function of this 1, 0 variable. And we said if we take the mean of a 1, 0 variable, that'll give us the sample proportion, because it just counts up the number of ones, or the number of people who have ever tried it, and divide it by the total number of people we have in this sample. So we'll take the average of this 1, 0 variable. That mean or that average will reflect to us then what the sample proportion was. Okay? So from our sample, about 34% of these students have tried e-cigarettes. Let's use this hypothesized true value of 0.25. Or let's do, kind of similar to the example that we actually just did. So we'll get more practice with this, but see how we do it in Excel. I'm erasing everything here. Let's assume that the null hypothesis, or what we want to test for is this true population proportion something greater than 0.25? So we'll assume the opposite is true. Or thinking about what this really means is the proportion, what we want to try to test for is the proportion of kids who have tried e-cigarettes greater than 25%, right? Or is it greater than a proportion of 0.25? We'll assume the opposite is true and look at our sample evidence and say, does the sample evidence go against that? Well, yeah, it's definitely not less than or equal to 0.25, but is it inconsistent enough with that assumed true value that we could actually reject it? Well, we have to work through, find our p-value or kind of find our critical values in order to make that rejection decision. So the first thing we want to do, no matter what approach we use, the critical value or the p-value approach, we need our test statistic. So we had this equation. Where was that? There you go. We have this equation for our test statistic. We're just going to have to use Excel as a calculator. So we're going to put this function into Excel, but we don't have to plug the numbers in. We can just select the cells that have our sample proportion, our assumed true proportion, and our sample size. So I'm just going to be entering that function into Excel here, that formula into Excel, I should say. So the numerator was take the sample proportion you found and subtract the assumed true proportion, which I put that value over here. Okay? And I'll show you why that's kind of useful if instead of just entering in 0.25 there. We'll then divide by the square root of that assumed true population proportion times 1 minus that assumed true population proportion divided by my sample size. Right? So I just took this test statistic equation and I entered that formula into Excel by clicking on the cells that had these values in them. So I'll hit enter here, and that should give me my test statistic. Now, if I look at this, what should the sign of my test statistic be? Well, if I think about what I'm looking at, and I'm going to erase the null alternative hypothesis here to give me some more room, because I know I want to do something else later. I've assumed from that null alternative hypothesis, the value I want to test against is that 0.25. So I've assumed that's what the true population proportion is. If in fact it was true, my sample proportion should be normally distributed around it. And I saw a sample proportion of about 0.33. I had a right-tailed test, so I'm thinking about my p-value would be the area to the right of that. Right? Well, I can't find that from a normal distribution very easily. But what I can do is turn this into a test statistic or a z-statistic and find the area to the right of that, right? Because that just represents my p-value. I've just converted a normal distribution into a standard normal distribution so I can use that table or the built-in functions in Excel, okay? So that's what I'm trying to do visually. So I've got this test statistic equation. Should give me my test statistic here. I get 2.02. But if I looked at what I had drawn up there, I found something above the mean, right? This was the mean of my distribution. If I find something above the mean, remember, the z-score of the mean should always be 0. So if I see sample evidence above the mean, I know that my z-statistics should be positive. if I saw something below the mean, I know my z-statistics should be negative. So one mistake I could have made here, and kind of remembering that would have prevented me from making that mistake, is let's say I'd forgotten to put these parentheses around what was in my numerator for that formula. Well, my order of operations there would then do some weird things and end up with negative 5.4. Well, if I look at what I had drawn, right, oops, I can get this up here for the video. Well, why is it not liking this? There we go. Remember, I knew that I was going to have a positive z-statistic. So if I'm doing this work in Excel and I see this negative value, I'm going to say, I definitely made a mistake. I go back in here. Order of operations is wrong. Let me fix those parentheses. Now it should be working correctly. Right? So I found this test statistic of 2.02. If I was doing this by hand, I'd go to my standard normal tables, look up this z value, right, the z statistic. It would tell me the area to the left. I want the area to the right, so whatever my table told me, I would just subtract that from 1. Well, how do we use those tables in Excel? Well, that was where we used that norm.s.dist function, right? I have a z value. I want to know the area to the left of it. Well, I actually want to know the area to the right, but I first have to use Excel to find the area to the left and then subtract it from 1, right? So here's my z statistic or my z value. I then put comma 1. So this norm.s.dist function will look up that test statistic of whatever it was, 2.02, spit back out at me the area to the left of it. Well, I wanted the area to the right, so the only other thing I have to do is subtract that from 1. Okay. Any questions on that? Check the chat here. Any other questions or? All right. So I get this p-value of 0.02. Okay. Now, if I just look at the 90% confidence level, what should my rejection decision be here? Well, if I have a p-value of 0.02 and an alpha of 0.1, we said we only reject if the p-value is less than alpha. So will I reject or fail to reject here? Is my p-value less than alpha? 0.02, yeah, is definitely less than my alpha of 0.1. So I can reject, but there's a kind of a neat way I could do this in Excel. So it's something we haven't looked at yet, which is the if statement. Okay? So if I know that my rejection decision is always going to be is if the p-value is less than alpha, I could say, okay, if, and the first thing this if function takes is, what am I trying to test? Well, I'm trying to test for whether or not my p-value is less, whoops, if I can hit the right thing, less than my alpha. If that's true, comma, what do you want to put in this cell if it's true? Well, I want to put the word, I have my caps, I think. I want to put the word reject in. Now, if I want this cell to display the word reject if the p-value is less than alpha, if I want it to display text, I have to put that text in quotation marks. So if the p-value is less than alpha, which it definitely is here, this cell should spit back out at me the word reject. I then put another comma. What if it's not? What if that doesn't hold? What if the p-value is not less than alpha? Well, then I want to put in the words fail to reject. Right? So this if statement, the first thing you tell it is what are you trying to check for? Well, here I want to say is the p-value less than alpha, comma, if it is, what do you want? What word do you want here? The word reject. If it's not, put fail to reject. Right? So sure enough, we reject here, right? Now, what if I put in an alpha of 0.05? What should I see displayed in that cell? Yeah, p-value is still less than 0.05, so I should see reject. What if I do an alpha of 0.01? Now my p-value is not less than alpha, right? So I should see fail to reject. Right? So that's kind of nice because I can change the alphas I'm looking at and get a really quick decision kind of there. And it's not just for me. If I'm trying to like show someone else, they could see that. Right? Now I could have also used the critical value approach, which the critical value approach was where we're looking at, let's say I don't see my test statistic yet. I'm looking for a critical value that gives me alpha in this tail. Well, I no longer have the z-value and I'm trying to find the area. I know the area I want. For us, I believe it was, we were doing a 90% confidence test, so 0.1. Right? So one thing with Excel is, just like the tables, it always works off of whatever the left side of the distribution is, or what the area to the left of this value is. So if I want the value that gives me alpha of 0.1 in my upper right tail, what I have to tell Excel is the area to the left of that, which would be 0.9. Or, how did I get that 0.9? 1 minus alpha. Right? So, I'm going to go back to this Excel file. What's the formula in Excel that if we tell it the probability, it gives us the z-value that gives us that probability in the lower left tail? It's not norm.s.dist. That was norm.s.inv, right? We're working in reverse. And the area I want in my left tail was not 0.01, it was 1 minus that. Right? And I think actually the original alpha we had started out with was 0.1. I was kind of showing you how that rejection decision formula would change. But right, we have to tell Excel what area we want in the left side of that critical value. So for a right-tailed test, we have to do 1 minus alpha. Okay? Now I could do the exact same thing and make rejection decisions down here. But now, now I want to test for if my test statistic falls anywhere in this rejection region, right, then I reject. If it doesn't, I failed to reject. So now what I want to test for is my test statistic greater than my critical value? Okay? So is it greater than my critical value? So if my test statistic is greater than that critical value, comma, if that holds, I know my test statistic is in that rejection region. Okay. So if that's true, put the word reject. If it's not, put the word fail to reject. Okay. Now this should, the critical value and the p-value approach should always give me the same rejection decision. So if I hit enter there, at the 10% significance level, they both say to reject. The 5% significance level, they both say to reject. At the 1%, they both say fail to reject. Right? Yeah.
So on the exam, doesn't matter which one you use, are you going to be like, use the...
So, yeah, once we get closer to the exam, I'll explain the format a little bit. Some of the questions I ask you specifically would be like, what is the p-value? Or what is the critical value, right? So I want to make sure you know how to do both. But I can tell you right now, there will be kind of a larger short answer question where I just ask you to provide support for what your rejection decision is, right? And you can choose either the critical value or the p-value approach, but you have to choose one and kind of show completely. And I'll have some specifics of like, you know, it's not just what's the rejection decision. You can write reject or fail to reject, right? I'll kind of have some prompts for what I want depending on which approach you choose. Does that make sense? Okay. So one thing that's kind of interesting here, if we go all the way out, instead of to the 90% confidence level, to the alpha of 0.01 would be the 1% significance or 99% confidence level. Even though I found a sample proportion that's pretty far away from that assumed true value, right? 0.33 is pretty far away from 0.25 when we're thinking about proportions. I still can't reject that the true population proportion is 0.25 or lower. Right? Now, that would be if I had a sample of size 100. If I take higher samples, what that's going to do is greatly reduce the variance I can see for my sample proportions. Right? So let's use the actual sample size of this data set. So instead of 100, let's use that count function and select the entire variable. So Control-Shift or Command-Shift on a Mac, down arrow. If I do that, I see, okay, I have 18,000 people. Well, now notice that sample proportion is now 27 standard deviations away from the assumed true proportion, right? Or the test statistic is, you know, almost 28. So here we're getting p-values that look like no different than 0. So with 99% confidence, even finding the same sample evidence, because my sample size is so much larger, I'm able to reject, right? And that's the idea that if I took a higher sample size, I know the distribution of my sample means is going to get a much lower variance or really peaked. And the only values I should be seeing for my sample proportion would be around whatever that true proportion is. So with that higher sample size, if I see 0.33, I know that 0.25 likely isn't what the true proportion is because I'm 27 standard deviations away from that, right? It'd be very unlikely. In fact, the probability that I saw 0.33 as my sample proportion, if in fact the true population proportion was 0.25, that probability is essentially 0. Right? That's what my p-value represents. And so if that probability is essentially 0, I'm okay rejecting it even with 99% confidence or a 1% significance level. Now notice what's kind of neat here too is I can start to do hypothesis tests because I use cell references at different levels. So what I'm saying here is I can reject that fewer than 25% of all these middle and high school students have ever tried to e-cig. I know that the true population portion is something higher, right? Based off the sample evidence I found. Well, can I reject that it's less than 30% of students, 0.3? Sure enough, I can still reject it based off the sample evidence I found. Can I reject 0.32? Sure enough, I can. Can I do 0.3333? That'd be 2/3. I can't quite do that, right? So I can kind of get to where I can reject a lot more values because I had such a high sample size. I know that based off the sample portion I found, with such a high sample size, the true population mean has to be somewhere pretty close to that. In fact, even 0.32, I could reject as being the true population proportion. Any questions on that before we keep moving here? Okay. I think that's all I wanted to say here. So we're going to take a step back, and this equation kind of comes from last class, but we said if we're doing hypothesis testing for a sample mean where we know the population variance, our test statistic was take the statistic we're interested in, the sample mean, subtract the assumed true statistic, or the population mean, divide by the standard deviation of the statistic you're interested in, so the standard deviation of our sample means, which we know is the square root of the population variance over our sample size. So we're going to do a hypothesis test for a sample mean example, and the only thing that really changes is we have a different test statistic equation. So let me zoom in on this so we can actually see it. But if you go over, you might have to, I think when you first open it, you might have to scroll over using these to this population variance known sheet. So let's say I have BMI here. Someone gave me the population variance, and I already calculated the sample size here was 145 people. If I wanted to find the sample mean, I would just use that average function, go over to the BMI variable, find the sample mean. Hopefully that part's pretty easy by now. Let's say I want to test against this value of 30, and I'm going to do a left-tailed test here. So I think the way that I had this set up was I want to test for whether or not the true BMI, population mean BMI in the US, is less than 30. So I'm going to assume the opposite is true, or that it's greater than or equal to 30. Right? So what type of tailed test do I have here? Well, there's a less than sign. So I'm thinking about, I'm going to have a left-tailed test. Right? I'm assuming the mean is 30. So my sample mean should be normally distributed around that. I found a sample mean of 29.5. If I wanted to find my p-value for a left-tailed test, that's the area to the left of the sample mean that I found. Well, how can I find that? I can turn that into a z-statistic, look that up on the table. For a left-tailed test, it's kind of nice because once I look up my z-value now, the table tells me the area to the left. Well, that's what I wanted for my p-value. Right? So makes life a little bit easier. But the first thing that we're going to need is what is my test statistic, right? Well, that was that formula I had up here on the board. So let me, for the video, after the fact, there we go. So it'd be kind of this guy right here. So I'm just going to say, okay, take my sample mean, subtract my assumed true mean, which I put in a cell up here, divide by the square root of my population variance, divided by my sample size, right? So I'm just using Excel to do kind of as a calculator or to do the math for me there, right? So I found something that's below the assumed true mean. So my test statistic should be negative, right? Remember we said whatever the mean is, that should have a z-value of 0. So if I find sample evidence below that assumed true mean, my test statistic will be negative. If I find sample evidence above it, that'd be a positive test statistic. So I'll hit enter here, and I get a test statistic of negative 0.77. Okay, so the p-value, I'm going to want to find the probability that I saw a negative 0.77 or anything below that. How can I do that in Excel? Well, just like in the previous problem, norm.s.dist, because I now know the z-value or the z-statistic, and I want to find the area to the left of it. So I'll select my z-statistic, comma 1 gives me the area to the left of that. Well, for a left-tailed test, now I'm done, right? For the right-tailed test, we had to once I found the area to the left, subtract that from 1 to get the area to the right. But for the left-tailed test, I'm done. I don't have to do anything else, right? So I get this p-value of about 0.218. So if my alpha was 0.05 here, right, what's my rejection decision going to be? Well, my p-value is not less than my alpha, so I should fail to reject. Right? Now I can set up an if statement just like we did in the previous one. So if my p-value is less than alpha, comma, if that is true, I should be rejecting, comma, if it's not true, I should be failing to reject, but we'll put fail to reject as what the cell shows us. So if my p-value is less than alpha, I reject. If it's not, I fail to reject. Right? Well, clearly here we can see that if I hit enter, we should see this cell say fail to reject, because my p-value is not less than alpha. Sure enough, it does. What if I want to instead find the critical value? So here it's a little bit tricky. I mean, we can find our critical values, but the rejection decision using the if statement, there's going to be something a little bit tricky there. Okay? So if I want to find the critical value, what I'm really saying is, what's the value from that standard normal distribution? That would be the cutoff value for the type 1 errors that I want to choose. So alpha of 0.05. Right? Well, now when I go to Excel, just like in the previous one, if I know the area I want in my tail, and I want Excel to tell me the z-value that would give that area in the tail to me, well, now for left-tailed test, I have to tell Excel the area in the left tail. Well, that's already there. That's what I want. So I want 0.05 in that lower left tail. So I use that norm.s.inv because I know the probability I want, or I know the area in the tail, which is just alpha. And I know that my critical values for a left-tailed test should be negative, right? They're coming from that left side of the standard normal distribution. Sure enough, I get negative here. Now notice actually, if I have my alpha of 0.05 for a left-tailed test, my critical value should be negative 1.64. If we go back to the other problem, if I had chose the same alpha here, I get that same critical value, but positive for a right-tailed test. Okay. I'm going to hit Control on that so I get rid of that change. Okay, well now what if I want to use that if statement for the critical value approach? Well, it gets a little bit tricky with a left-tailed test because what do I really want? Well, if my test statistic is here, it's in the rejection region, right? So if my test statistic is, remember, these are negative values. So I actually want to see if my test statistic is less than my critical value, then I want to reject, okay? So now it's a little bit different than what we had before because we're dealing with the left side of the distribution, which are all negative values. So now I want to say if my test statistic is less than my critical value, right, which would kind of translate to being like a more of an extreme negative value, right? Well, now if that holds, I want to put the word reject in, and if it doesn't, I'll put the word fail to reject, right? So same kind of idea. It's just now the if statement, we're not checking if the p-value is less than alpha, we're checking if our critical value, right, is kind of smaller than our test statistic, or said differently, our test statistic is less than that critical value. So I'll hit enter here. Sure enough, I get the same rejection decisions. Okay? Where are we on time here? Oh, a couple minutes. Okay. So one thing you could also do, just since we have a little bit of time, I want to kind of highlight this. One thing you could also do here is, right, we fail to reject, right? So we can't say that the true BMI in the US is not greater than or equal to 30, based off the sample evidence we found at the 95% confidence level. In fact, we can't really do it at any of our conventional confidence levels. But one thing with this if statement you could also have done, notice, I said this last week, you can always check to make your rejection decision if the absolute value of your test statistic is greater than the absolute value of your critical value. So it's a lot of values in there, but if we take the absolute values of these, essentially that just becomes the right side of the distribution, and we could write it out just like we did for the right-tailed test, which was if once we take the absolute value, just check to see is your test statistic greater than the critical value, right? So if we take absolute values here, we would actually we just say, is the absolute value of our test statistic greater than the absolute value of our critical value? And the reason why this is kind of helpful is because if you always write it this way, well, if I were to put the absolute value function on a right-tailed test, it changes nothing, right? If I put it for the left-tailed test, it kind of allows me to always say, is the test statistic larger in absolute value than the critical value? And this also helps me once I get to a two-tailed test as well. Because remember, for a two-tailed test, I have two critical values, so I could be checking something on the left or on the right. And so this is just kind of like a nice way to kind of fail safe against that. If I take the absolute value of my test statistic and the absolute value of my critical value, no matter what type of tailed test is, or what type of tailed test I have, once I take the absolute value, I always want to be testing for this. If the absolute value of my critical value is less than the absolute value of my test statistic, I'll reject. Doesn't matter what type of tailed test I have. And so doing that is kind of a fail safe. Otherwise, you kind of have to like draw it out and like, oh yeah, these are negative values, so I need to know is it less than, and it gets a little bit harder there. Okay. I think that's all I wanted to say here. And if you set it up this way, you can always play around with different values. I can reject 35 even though I couldn't have rejected 30. I can reject 34, 33, 32, maybe even 31. Yeah, actually 30 was the one. Oops, I put it in the right cell here. 30 was the last one that we couldn't reject. So it's kind of useful to use those cell references so you could start to do hypothesis tests at a ton of different values really quickly, right? And not only that, then you could start to change the level of confidence that you can make your rejection decision at pretty easily if you had a cell reference for alpha as well. Okay? Any questions on that before we kind of get out of here? All right, so I'll get an online quiz up there today. Should only have like one question. Just to kind of make sure we're all following along with this. Next class, we'll just keep doing more hypothesis testing. We'll do some examples where we don't know the population variance, and then we'll kind of see how we would do that in Excel. And then from there on out, it's really just, I'm going to be bringing in more hypothesis testing examples, showing you how to think about hypothesis testing in a couple different ways. So hopefully just get more experience going into that second exam so that everyone kind of is prepared and does well. Okay? All right. I will see you on Wednesday.